Welcome to Late Night Chemistry with Mr. Harden. Today's episode, Polar Molecules. So when you think of the word polar, it means something with two opposite ends. You could think of the Earth with its North Pole or South Pole, or a battery with a positive end and a negative end. Those items are both polar items. In terms of chemistry, a polar molecule is going to be a molecule that has a positive end and a negative end. The simplest example would be a molecule such as hydrogen chloride, HCl. You can see the Lewis-Dot structure. There's not really a central atom, but anything connecting 2 points together is going to be a straight line. So here's the three-dimensional shape. The electrons that are in the bond between hydrogen and chlorine are shared between the two atoms, but they're not shared evenly. Chlorine is more electronegative by far than hydrogen, so electrons experience a greater pull toward chlorine. That results in having a negative charge. Now, there's a strange little symbol by that little negative. That's a Greek letter delta, which is used to indicate a partial negative charge. If I just wrote down a little dash there for negative, that would be -1, like you'd see in sodium chloride. That would be great if chlorine actually had stolen an electron from hydrogen, but it just experiences a little bit more of those electrons than hydrogen does. So it does have a charge that's negative, but not a full -1, so somewhere between 0 and -1 charge. That's what that little symbol means. It's used to indicate a partial or a fractional negative charge. Now, if the electron is being pulled away from hydrogen, well, then hydrogen's going to end up with a partial positive charge. In case my little symbols are hard to see, all that little symbol is the lowercase Greek letter delta, fourth in the alphabet. So here are the steps to determine if a molecule is polar or nonpolar. Well, the first is to draw the Lewis-Dot structure. The Lewis-Dot structure is used to come up with the three-dimensional shape using VSEPR theory, what we just did in our lab. After that, you're going to place the partial positive and partial negative charges. The most electronegative atom will get the partial negative charges, and the least electronegative will get the partial positive charges. If it has a positive end and a negative end at this point, well, then we call it polar. Let me just adjust this a little bit. If it has a positive inside and a negative outside, or negative inside and a crunchy positive outside, well, then we just say it's nonpolar. There's not a definite positive end and a definite negative end. Let's look at a couple examples. Okay, boron trifluoride is our first example. Step 1, drawing the Lewis-Dot structure. Something you definitely should know how to do. Step 2 is three-dimensional shape. Now, boron has 3 electron domains, which makes it have a Y shape. So we draw the three-dimensional shape of boron trifluoride. Now afterwards, we can add in the partial positive and partial negative charges. Now fluorine is the most electronegative atom, so we'll put little partial negative charges for fluorine. So these are all these little partial negative charges. And boron, being less electronegative, get a partial positive charge. The conclusion. Well, there's not a positive end and there's not a negative end. There's positive in the center and negative all around, but inside and outside are not ends, so this will qualify as something that is nonpolar. Now, a note, when you're doing these things, you do not have to redraw boron trifluoride, the three-dimensional shape, 3 times. From the Lewis-Dot structure, you could draw it once, add in the partial charges, and then come up with the conclusion. So one Lewis-Dot drawing, one 3D shape would be sufficient work. I just have it drawn multiple times so I can show you it as step-by-step process. Let's look at another one. Water. Step 1, Lewis-Dot structure. Step 2, three-dimensional shape. Since water has 1, 2, 3, 4 electron domains, the basic shape is that tetrahedral shape, but when you knock off 2 of the sides where we have bonding pairs for non-bonding pairs, you get left with the bent line, or the V shape. If you flip it upside down, it'd be a V. You add the charges, the partial positive, partial negative charges. Oxygen is more electronegative, so it's partial negative. Hydrogens are more positive, you get a partial positive. Top is negative, the bottom is positive. That makes water a polar molecule. This would be a good time to hit pause. So you could try sulfur dioxide on your own. After a brief period of time, we will go and actually do this. I'll show you my solution to it, but you get a lot more out of it seeing what you can do on your own. Okay, this is my solution for sulfur dioxide. First, draw the Lewis-Dot structures. Now, you could represent the bonds in sulfur dioxide either with the partially ionic, partially covalent bonds, or if you represent all the bonds like they are covalent. Either way, there's 3 electron domains. Any bond between 2 atoms counts as 1 electron domain, and any non-bonding counts as electron domains. So sulfur, regardless of which way you're representing it, in sulfur dioxide ends up with 3 domains. 2 for the bonds, 1 for the non-bonding pair. Now, 3 electron domains makes it Y-shaped, but you take away one part of that Y shape for the non-bonding pair, which results in a V-shaped or a bent line molecule. Now, oxygen is more electronegative, so it ends up having the partial negative charges. Sulfur is less electronegative, so it has the partial positive, positive top, negative bottom, makes it polar. Now, here's some good news. If you get your electronegativities wrong, it still works. Because if you accidentally said, well, sulfur should be more electronegative and oxygen less electronegative, which is not true, but if you did that, you would just have partial negatives at the top and partial positive at the bottom. And even though that's incorrect, you come up with the same conclusion. It's polar. Because being polar is being caused by a combination of the difference in electronegativities and in the shape. And even if you have the comparison wrong with electronegativities, you still have a difference. So it's a little bit forgiving, which is a nice thing. So let's look at the next one. Okay, carbon tetrachloride. This would be a good time to pause so you come up with. In a moment, you'll see my solution. Okay. So, carbon tetrachloride. Carbon has 4 electron domains, which makes it tetrahedral. Chlorine is more electronegative, gets the partial negative charges. Carbon's less, so gets the partial positive. You got partial negatives all around, partial positive in the center. That means there's no one end is positive, another end is negative. It's negative on the outside, crunchy positive center. This will be nonpolar. Okay, I think you know the drill by now. I'm going to show you one. You should pause it, work it out, and we'll see what the solution is. Compare what your solution is to mine in a minute. Okay. Sulfur tetrafluoride. You could represent it like the bonds are partially ionic, partially covalent, or all the bonds pretending like they're all completely covalent. Either way, you have 5 domains, which is the trigonal bipyramidal sort of shape. There's one non-binding pair, so you remove one of those parts to that shape. On the sides, where there's the most room, you end up with everyone's favorite shape, seesaw. Okay, if you would rotate this 90 degrees, it would indeed look like a seesaw. Now, this one, it may be hard to see when you put the partial negatives, partial positives, that it's polar. So one way of seeing it is like this. Sulfur is partially positive. You can't say the top, and all the fluorines are partially negative. You can't say the top or bottom would make it polar because it's both negative. But if you look at left or right, you got the fluoride side, you got the sulfur side. The sulfur side's positive, fluoride side's negative, so it's polar. The other way of seeing it is something is polar if there's a net pull of electrons in one direction. So, in this diagram, you can see the electrons are being pulled toward the fluorines. Now, pulling straight up and pulling straight down, that pull will cancel each other out. And then you've got these two pulling it toward, the left. Now, in 3 dimensions, one would be coming out of the page and one would be going into the page. The out and in part would cancel each other out, but still there's a net pull toward the left. If there's a net pull, that's another way of seeing that it's polar. CH2Cl2, dichloromethane. So pause, work it out, unpause it, check your answer. Okay. So we have Lewis-Dot structure, though maybe a little bit lazy, and I should have put little dots around all the chlorines. The outer ones, that's a small mistake if you leave it out of the outer ones. If you leave electron pairs out of the inner one, you're going to lead to the wrong shape. That would be a big mistake. I draw the 3-dimensional structure. Well, you got 4 electron domains, so I could draw it like this. Now, this might be hard to see just because this is imagining a 3-dimensional shape and it's drawn in 2 dimensions. All the chlorines being partial negative and the hydrogen partial positive are simple enough to do. This bottom chlorine is supposed to be drawn, so it's actually coming out of the page toward you. And this hydrogen on the left-hand side is going basically into the page. Well, in that case, this area between these 2 chlorines up over here in the front of the page is where the negative part is. And then between the two hydrogens in the back of the page is where the positive part is. It makes it polar. Now, if you had the same thing, but you just spun it around a little bit. So this chlorine was spun around, so it ended up over here. And this hydrogen went over here. You spin up the axis, so this chlorine is in the top is not really changing. You're just doing a little spin in this little molecule. This drawing is a little bit easier to see. It's the exact same thing. If you had a three-dimensional model, same model. But sometimes where you choose to place things make it a little bit clearer. So it's not changing whether it's polar or not. It's indeed polar, but it's a lot easier to see now that these partial negatives are, on these two, and the partial positive there to see that's the negative side and that's the positive side. So dichloromethane, polar molecule. So I always enjoy asking questions. Are any shapes automatically nonpolar? So this is a pause, not for dramatic effect, but to give you a chance to think. In general, the answer is no. For example, carbon dioxide and hydrogen cyanide are both linear molecules. You could draw the Lewis-Dot structures out. And they have two domains each, so they're be lines. But in carbon dioxide, because you've got oxygens on both sides, that's being partial negative, and carbon in the middle being partial positive, there's no positive end or negative end. It's nonpolar. Hydrogen cyanide, the least electronegative is hydrogen, that's a partial positive. The most is nitrogen, that's the partial negative. That's a positive and a negative end, that's polar, even though they're the same shape. So, because of this, you can find anything that looks shaped that looks really, really symmetrical, but if you have different atoms on the outside, they'll probably end up being polar. Now, if all the atoms are identical, like they are at the outer atoms, like they are in, like, say, carbon dioxide, then shapes like the line and the Y shape and the tetrahedral and the trigonal bipyramid and the octahedral and the square or X shape, whatever you want to call it, those would end up being nonpolar only if all the atoms around that central atom are the same. So, are any shapes automatically polar?